Hello, I'm Tom Sugar. I'm a professor at ASU, the Polytechnic campus, and today I'm going to talk to you about helper robots. These robots help humans in navigation, automotive systems, and manufacturing. What does a hugging robot teach us in terms of human-robot interaction? In Henny Benamore's lab, it can teach us and robots a lot about close interaction with each other. It teaches the robot how to assess its human partner. How reluctant is the human to be hugged? How fast is the human? What hugging motion does the human perform? When should the robot react? Another key component of Benamore's focus on human-robot interaction is intention prediction. How does the robot understand what the human is going to do? When the human and robot are working collaboratively on a task, such as adding parts on an assembly line, how does the robot adapt to changes in rhythm? Benamore and his team are investigating machine learning algorithms that can be adapted for close contact interaction scenarios. The suckermouth catfish was the inspiration for the fish-inspired robot for extreme environments, known as the Fire Robot, in Assistant Professor Daniel Aukas's Idea Lab. And like the scavenger's catfish are known to be, Fire's future is in cleaning canals and waterways that require navigating through tight spaces. Fire is equipped with independently controllable caudal and pectoral fins, enabling it to navigate in extreme environments like canals, using complex swimming gaits such as flapping and paddling. This enables Fire to perform a full turn with a near zero turning radius, even under turbulent conditions, and it can also maintain speed and direction despite opposing current, and can reach speeds up to 28 yards per minute. But the novelty of Fire is its simplicity, not its complexity. The Idea Lab team used origami techniques and affordable, flexible, lightweight materials to make Fire's mobility truly unique. Fire may be programmable like a robot, but it swims like a fish. It may seem like drones are everywhere. The reality is they are not. There are still narrow and cluttered spaces where hardscapes do not allow them to travel. In Wenlong Zhang's Robotics and Intelligent Systems, or RISE lab, they are creating a new category of robots that can morph and adjust to the environment. Zhang describes these drones as able to mimic bird-like flight, able to squeeze and fly through narrow spaces, and then return to full flight capacity. Using torsional springs and onboard cameras, a flexible drone can work with its human counterpart on projects like search and rescue missions in heavily forested or cavernous areas, or inspecting underground mines and damaged buildings in reduced lighting. A combination of rigid and flexible joints provides collision resilience and enables the drone to maintain stability. The next project in the RISE lab is drones made completely from soft materials and compliant actuators, which will give them even more flexibility. Professor Aviral Shrivastava's Make Programming Simple lab is working on cooperative algorithms for autonomous vehicles. Auto manufacturers want to make sure that their autonomous vehicles aren't responsible for accidents, says Shrivastava. But the manufacturers are working independently rather than cooperatively, and communication is the key. Shrivastava's lab is working on a broad-based platform through which different manufacturers' vehicles can communicate effectively with each other, with humans, and with the environment. The range of issues being investigated to create a universal communications platform includes: what do autonomous cars need to tell each other? What communication systems work most effectively? How is information from human-driven cars processed? And how are environmental factors incorporated into decision-making? The goal is to make the blame-free algorithms developed by Shrivastava's team so attractive that they will be universally adopted. And as communication tools between autonomous vehicles improve, so will collaboration between the manufacturers.